So I was thanking the organizers for invitation to Padova, and I will try to be fast because everybody wants to finish this conference, including myself. So, many of the things I'm going to say today have an overlap with what Zoltan was explaining yesterday, but I think it's important to go through interesting themes a couple of times. So my starting point here is going to be very traditional. It's going to be perturbation theory. I mean, we like perturbation theory because it's a universal tool, it's analytic, but perturbation theory has an original sin, which is it never gives you the exact, it almost never gives you the exact result for an observable, because perturbation theory gives you only asymptotic approximations to observables. So you want, for example, to compute the ground state energy in a quantum mechanical problem as a series in the coupling constant, you will find that the coefficients grow factorially, so this series is asymptotic and it's not really representing a function. So this is not, you cannot really even write a sign of equality here. You only have an asymptotic approximation. And the asymptotic character of the series is related to the existence of non-perturbative effects in quantum theory, which go typically beyond perturbation theory, and they are exponentially small more often than not in the, in the coupling constant. So the typical non-perturbative effects I will consider here, and the ones that you really find experimental in quantum field theory, are exponential effects in e to the minus a over g, where a is a constant, and you see that this is non-analytic when g is equal to 0, and this is invisible in conventional perturbation theory. So what do you expect is that if you wanted to compute a physical observable, you would have something like this. You would have to add the knowledge, the perturbative knowledge that you have, and then you should add some exponentially small corrections. And this actually is the answer that is suggested by the saddle point method when you apply it to the path integral. So if I write this equation explicitly, I would write my observable as the perturbative series I had before, plus a bunch of exponentially small corrections, which, by the way, involve themselves infinite series in the coupling constant. So you have an exponentially small term here, which is non-analytic, but then it will be multiplying a power series in G. And this is the kind of picture that you would find as saddle point approximation. So you could think about the perturbative series as coming, say, from the leading saddle point, and then additional saddle points would give you this kind of additional term. Okay? So this is roughly the idea. But of course, you know, this idea has to be qualified in many ways. But the most important thing is that this kind of fundamental object that includes the perturbative series plus this non-perturbative part is something which goes beyond traditional series, has a special name, which we call trans series. Okay? So this was a term introduced by Jean Eccal, which is the mathematician who formalized many of these things. And what is very surprising about the trans series is that, if you think about it, is that we know how to calculate the perturbative part because our main quantum field theory textbooks have many chapters on doing renormalized perturbation theory, but there is no chapter in our textbooks about how to calculate the exponentially small corrections. I mean, there is no chapter in Peskin and Schroeder which tells you how to calculate this. You have many chapters on how to calculate this, but it's natural to add these two things, but you don't really know how to do this. And this is just already, I can already tell you what is the fundamental challenge here. The fundamental challenge, because this is a conference on fundamental challenge in theoretical physics, the fundamental challenge is to develop a systematic theory of non-perturbative effects and trans series in such a way that when you get this trans series and you manipulate it correctly, you will get actually an exact equality, an exact result for the observable. Not just an asymptotic approximation, but an exact result. Okay? And this is the program that many people have started. It's sometimes called the Resurgence program. Also, I will qualify this in a little moment. But before telling you what are the challenges ahead, let me just give you a brief review of what is known. What do we really know about non-perturbative effects and trans series in quantum field theory, for example? As I said, this is not really chapters in the standard books, but this is really an old problem. And this problem was already started, people started to think about this problem already in the 70s and 80s, so this is really a traditional problem in theoretical physics, but I think it's still not completely clear how to go about it, and I will try to give you a perspective on this. Okay, so there is a first tool that I'm going to use in order to have some knowledge about non-perturbative effects. And this is one of the things that Zoltan was explaining just today. It turns out that one way of learning about non-perturbative effects in physics is by using perturbation theory. And the good thing about this is that this can be made mathematically very precise, and since I'm a mathematical physics, I like this type of problems. So I'm going to give you in a very short summary of how this goes, and this repeats many of the things that Zoltan explained yesterday, but I'm sure that we wouldn't mind going through them again, because it's relatively complicated. So let's suppose that we start with a formal power series, which has coefficients an, which diverge factorially. So this series, as I said, doesn't really define a function. This series has zero radius of convergence, so you don't really know what to do with it. And as Zoltan was mentioning yesterday, what you can do is to do a Borel transform. This is a radical surgery operation in which you divide every coefficient which goes factorially by n factorial. So these coefficients now, after divided by n factorial, will typically grow only exponentially. And then you introduce a new variable, so introduce a new function, and this function is going to be convergent in a neighborhood of the origin, typically. So this is fantastic because you go from the uncontrolled walls of asymptotic series to the controlled walls of analytic functions. And if you look at this Borel transform, it's going to be analytic at the origin, but then once you move away from the origin, you are going to start to find singularities in the complex plane. And these singularities can be of all kinds. You can have poles, branch cuts, and so on. So generically, you expect something like this. So sigma omega here, omega is an index, so sigma omega prime, they know the position of singularities. And I want to emphasize that these are things that you can actually compute realistically if you know enough terms of your perturbative series. So this is a plot of the structure of singularities in an actual physical example. I think this comes from cyber-weighted theory. But these are things that you can really calculate, and you can see the position of the singularities by doing numerical calculations. So this is not something abstract, it's something that you can really implement. Now, once you have this, it turns out that these singularities are really crucial for the game, because these singularities are going to have the information about the non-perturbative effects. And what you have to do, I mean, I'm not going to give you the details. Zoltan tried to give some of the details yesterday, but it's really slightly complicated. But the main message of this is that the local structure of this Borel transform around these singularities has information about new sectors of your theory. So essentially, a local analysis of the Borel transform of each of these singularities will give you two pieces of information. It will give you a new power series that I denote here by phi omega z. And if you normalize this power series correctly, you will have some sort of overall constant, which is going to be important in some of the applications, which is called sometimes Stokes constants. And these are information that is intrinsic to this Borel transform. So if you know the perturbative series in enough detail, you should be able to extract this information. Okay? So this is local information of the Borel transform that you can find with complex analysis. Now, once you get this information, you build up a non-perturbative object, which is simply an exponential of the location of the singularity divided by z. So this is the non-perturbative effect that I was mentioning before. Then you will have some sort of loop expansion around this effect. And then you will have an overall strength of this series given by this Stokes constant. And of course, this Stokes constant depends on how you normalize this series, but sometimes there are natural normalizations of the series which give you natural normalization for these Stokes constants. And so, and what I want to insist is that this is a well-defined mathematical problem. You take your favorite power series in your favorite quantum field theory, in your favorite string theory, and this problem is with very mild mathematical assumptions. It's a problem that can be solved. Okay? You can actually find all these series, and the collection of power series as the Stokes constants that you find in this way is what we call the Resurgence structure of the perturbative series. Okay? One way to get this information is by looking at the large order behavior of the perturbative series. It can be very easily seen that this information about the singularities is equivalent to knowing the large order behavior of the perturbative series. But this is a well-posed mathematical problem. So one mathematical challenge is, given your favorite theory, how you would extract all this information. But what we are interested in here is what we can know physically, what we can learn physically from this structure. Okay? So this is, as I said, this has a long history that goes back to a very nice paper by Bender and Wu in 1971, where they tried to solve this problem in the simplest context possible, which is ordinary quantum mechanics, stationary perturbation theory in quantum mechanics. So they look at the simplest problem in perturbation theory in quantum mechanics, which is the anharmonic oscillator. So you have a harmonic oscillator here, and then you perturb with a quartic term, and you can compute, for example, the ground state energy of this system by a power series in G, and this is an exercise that we regularly give to our students in graduate courses in quantum mechanics. So, as I said, this is a well-posed mathematical problem. What is the resurgence structure of this series? And actually, Bender and Bu essentially solved this problem with a mixing of numerical and analytic techniques, and they found that there is going to be a singularity in this Borel plane, in this Borel transform, of -1/3, so there is going to be an exponential term e to the 1/3g's, and notice that this is positive with a prefactor, and then there will be an additional power series that I didn't write here. So what's the meaning of this? What's the meaning of this trans-series, this non-perturbative thing? Well, this is actually a signal of tunneling in this problem. Why? Because if you change the sign of G, and this potential will go back, and then the ground state will be unstable, and it will tunnel, okay? And there will be a beta value KB effect that you can compute, and you see when G is negative, this becomes an exponential of something negative, and this is actually the exponential rate of decay for this problem. So you can discover non-perturbative effects like tunneling, which is the quintessential non-perturbative effect in quantum mechanics, by doing this game. Okay, so this is in a sense the simplest example, and we already learned something. If we didn't know about tunneling, you would have discovered it in some way by doing this analysis here. Okay? Now, finding the resurgence structure of a given series is a well-posed problem, but very challenging. Now, in realistic field theories, one question you can ask is, what do we know about this problem in realistic field theories? Now, we have only hints of this structure, and usually are based on approximations, like, for example, large N. Now, one thing that, so as I said, this is a traditional problem which goes back to the 70s, but one thing that we have learned in recent years is that maybe we can try to make progress in this type of problem by looking at sufficiently simple quantum field theories. For example, topological field theories are a good candidate to try to understand this, because topological theories, in some cases, we have control over the perturbative series, and at the same time, this is sufficiently simple as to make progress in this. And another place in which we can try to understand things is integrable, for example, two-dimensional quantum field theories, and this is something that Wagner was telling us about yesterday. So let me tell you a little bit about what you can actually learn in solvable examples. So I'm going to give you an example quickly, an example in topological field theory. So the topological field theory, which has a nice perturbative expansion, is Chern-Simons theory. So I'm going to give you an example in complex Chern-Simons theory. So you can now take complex Chern-Simons theory, which is a gauge theory in 3 dimensions, and you can do a standard perturbation theory around the trivial connection. Okay? So the trivial connection will have a perturbative series in the coupling constant, and it turns out that this expansion should tell you about non-perturbative sectors of the theory. And it turns out that in this case, you can actually see that if you expand around the perturbative connection and you try to see this non-perturbative structure, I'm choosing here a very special example where I do complex Chern-Simons theory on the complement of this hyperbolic knot. So this is an open 3-manifold. Now, you can actually find the resurgence structure in this example very explicitly. You find towers of singularities here. And what is very beautiful is that these singularities, the location of these singularities, which, remember, is the strength of the exponential effect that is going to be associated to them, is the volume of the hyperbolic manifold, which is the complement of this knot. So this is actually non-trivial, because this is the action of a gravitational instanton in complex Chern-Simons theory. This is the connection that represents the complete hyperbolic metric on the complement of this knot. So you really learn about new non-perturbative sectors of this theory by looking at the trivial perturbation theory. And this case is even more exciting because you can actually guess or compute the Stokes constants, and they turn out to be integers related to BPS state counting. So these Stokes constants that appear in the problem that I was mentioning before, it turns out that in topological field theories have a topological meaning. They are integer invariants counting objects in actually a dual supersymmetric theory to here. And this is actually some new insights that came in the theory of resurgence by applying to this type of examples. Theory of resurgence is an old theory that comes, as I said, from the 70s. By applying to new topological models, you can learn things that are quite surprising. You can actually, in a sense, discover new topological invariants by doing this type of analysis. Now, what can we learn from this study from Resurgence? Now, one thing that we learn is that instantons, non-trivial saddle points of the path integral, are a source of non-perturbative effects. This we knew before. It's confirmed in the example of quantum mechanics that I showed you, that I just showed you, and it's confirmed, for example, in this compression-Simons context. But one very interesting lesson of Resurgence is that it shows you that in many realistic field theories, there are non-perturbative effects, there are Borel singularities associated with Borel singularities, which are not due to instantons. This is a very important point that people who have worked on QCD know very well, but people who have worked on string theory are maybe not that familiar with. And these additional Borel singularities are sometimes called renormalons. And in QCD and in other asymptotically free theories, these, the Resurgence structures associated to renormalons are able to detect non-perturbative effects which are not due to instantons, which are due to vacuum condensates. Okay? So they are due to non-trivial vacuum expectation values of operators in the vacuum of these theories. So let me give you, again, a very simple example. So imagine that you consider, you can do it in QCD, but you can also do it in simpler theories like the Gross-Neve model. Suppose that you calculate the quark self-energy in a theory in which you have fermions interacting with some other field. This could be this line. So you have this is a quark self-energy, so you have a quark anti-quark two-point function, and here you have an interaction of this quark with some other particle. It could be a gluon, or it could be a scalar particle in the Gross-Neve model. And these type of diagrams, you can see that they lead to a Borel singularity. So they are diagrams that appear in perturbation theory, will lead to factorial growth, and they will lead to a Borel singularity. And the corresponding non-perturbative effect is actually related to a quark condensate, to the fact that quark, anti-quark operators have a non-trivial vacuum expectation value in this theory. And this, of course, in QCD is very hard to test, but recently with Ramon Miravillas, who is here in the public, we actually verified this very explicit in the Gross-Neve model, which is a toy model for the quark sector of QCD. But the general lesson is that when you look at these Borel singularities, you will find things which are not telling you about additional saddle points of the path integral, are telling you about other things. So let me now make a warning, a very important warning. So far, I have told you how to use the behavior of perturbation theory and these Borel transforms to learn about non-perturbative effects. But it's very important to notice that not all non-perturbative effects can be detected by these Resurgence structures. There are non-perturbative effects that are totally invisible when you look at perturbation theory. And there is a very simple example, which are theta angle effects. So theta angle effects are totally invisible in perturbation theory. And for example, you have an instanton that couples to the theta angle. You will never see this in perturbation theory. So Resurgence is a powerful source of information in the construction of a theory of transeries. But it's not the whole thing. It's just a method of detection, a very important one, but it's not really a theory of non-perturbative effects because we know that there are non-perturbative effects which are going to be missed in this way. Now, when people try to go beyond perturbation theory already in the 80s, there were actually two theories that were proposed to do this. And you have probably been exposed to some of these theories. One of them is instanton calculus, and the other is what I would call condensate calculus, which was introduced by Sigma, Weinstein, and Sakharov, mostly in QCD, to actually calculate effects due to vacuum condensates and so on. Now, these theories are very impressive. They have obtained some very successes, some important successes. But my feeling, and that's why I'm giving this talk, is that they are probably incomplete, they are insufficiently tested, and I think they are not fully understood, as I will argue in a moment. And remember, I want to make some connections to people that have talked before in this conference. Jan de Boer was mentioning how, in doing calculations with instantons in gravitational theory, sometimes one has to consider off-shell configurations, and this was not very clear. He was asking, what are the rules of the game for this? Actually, off-shell configurations in instanton physics are generic. Even in quantum mechanics, if you want to consider multi-instanton configurations in quantum mechanics, you have to consider off-shell configurations. So the rules of the game for doing instanton calculus are not really even, I would say, completely understood in quantum mechanics, not even to think about quantum field theory. So I think it's really important to revisit these things because we talk about instantons, but sometimes we don't really know very well what we are talking about.
Sorry, Mark.
Yes. Sorry? Yes.
Like written over there and so on. You were saying that there is no possibility to going back to the base and do resurgence structures at the moment?
In perturbation theory, you will not see it. In perturbation theory, around the trivial vacuum, okay? Okay? That's a fact. Also, effects due to chiral symmetry breaking are not visible in conventional perturbation theory. Now, let me make a remark about string theory. So, the genus expansion in string theory not only grows factorially, it grows doubly factorially, and this is something that we know due to the work of Gross and Peribal and Schenker. So resurgence, the techniques of resurgence should be also very useful in string theory and should give you information on non-perturbative effects. And this was actually one of the motivations for Polchinski to introduce the brains. One of the reasons that Polchinski introduced the brains was that this was going to be a source of non-perturbative effects in string theory. Now, there are many interesting results in the case of non-critical strings, and this has also a long tradition, starting with works by Saint-Just, Enach, and other people. And recently have been many impressive progress by Ricardo Schiappa, who also here in the audience, and his students, where they have actually, in a sense, fulfilled the full program of computing all the Stokes constants in non-critical string theories. And there is a more complicated theory than non-critical strings, where there has been a lot of progress in understanding the resurging structure, and this is topological string theory in Calabi-Yau manifolds. And I don't have the time to talk about this here, but I will talk about this in Strings 2024 if you are going to attend or you want to see the conference. So I will give you more detail. I will give more details about this in that talk. But one thing I can tell you is that we have a conjectural complete description of the resurging structure of topological string theory on any compact or non-compact Calabi-Yau, and we know exactly we have a conjectural prediction for where are the singularities, what are the transitions, and so on. So there is a complete conjectural solution for the problem of finding the resurging structures in the case of topological string theory. Okay? Okay, so this is in a sense what we know, and let me now try to pass to I want to make now a self-criticism session, because I think it's very important when you propose a program to be able to reflect why do you want to do this, right? I mean, this is something that we should all do at some point. You know? Why do you want to do what you are doing, right? And I think that's important. So why to bother about all these transseries? And after all, you know, you could go non-perturbatively without doing any of this. You can do a more direct approach which avoids perturbation theory completely. And you know, you can do lattice, and we have heard today about, you know, for example, using machine learning tools in quantum physics. Why should you bother about all these perturbative series and completing these different series? Just go directly to the lattice or go directly to the bootstrap and so on. Okay, let me give you 3 reasons why there is still maybe interesting to do what I'm proposing. Well, the first reason is that transseries are intrinsically analytic objects. And sometimes we can even do back-of-the-envelope calculations. So you take a person who is working in QCD, you know, she or he will be able sometimes to give you an estimate of non-perturbative effects in QCD by doing a back-of-the-envelope calculation using resurgent techniques. So this is still important. We can do analytic techniques, analytic calculations, and sometimes they are very simple. Now, a very important reason for me is that resurgence gives you a semi-classical decoding on non-perturbative physics. When you look at a transseries, you know what are these things. You know, the perturbative series is something that you can think about in terms of small perturbations around the vacuum. So they are like implemented through Feynman diagrams. Then, you know, instantons or condenses, you can also visualize them in some way. So we have pictures for these things. And this is also related with what Alejandra was also mentioning yesterday. Remember that she was giving these partition functions for minimal models and so on, and she was decoding these partition functions in terms of a gravity theory. So you have this kind of box coming from the 2D CFT, which are these sums over characters, but then you decode this as a sum over saddle points in gravity. This is the kind of semi-classical decoding that resurgence gives you. And the third reason, you know, and this is like all, beauty is always in the eye of the beholder, but resurgent structures are really fascinating mathematical objects. I mean, you know, the structure of transseries appearing in the Borel plane, all these Stokes constants that sometimes can be integers, can be topologically managed. This is really a fascinating mathematical problem which links complex analysis with the theory of resummation, with sometimes geometry and topology. It's really very fascinating. And remember, we have heard a lot about using computers in physics, and I'm the first one to use computers in physics, but also remember what Wigner said when he was shown a calculation from the computer. At some point, there was a computer, calculating some spectrum in quantum mechanics, and they gave Wigner the result of the calculation, and Wigner looked at it and said, well, it's very good to know that the computer understands the calculation, but I would like to understand it me too. So let me now run some challenges for the future. Now, instanton calculus, as I said, I mentioned all the problems with instanton calculus. We understand it very well in supersymmetric theories. And one of the reasons that we understand very well instanton calculus supersymmetric theories is because at some point we had an exact model for instantons, which was Seiberg-Witten theory. Seiberg and Witten predicted the whole structure of instanton sectors in n equal to super-Jarmals theory. And using this, there were a lot of activity, and this culminated in the work of Nekrasov, which gave a full microscopic understanding of this. Now, the problem is that in realistic quantum field theories and non-supersymmetric quantum field theories, we don't have such a toy model. We didn't have such a toy model until very recently. And I want to propose, in a sense, what I think right now could be the analog of Seiberg-Witten theory for non-supersymmetric theories, and this is the O3 nonlinear sigma model. And in the O3 non-sigma model, you can actually calculate, I think Zoltan was talking about this, you can calculate this free energy in the presence of a chemical potential. And recently, using integrability, instanton amplitudes have been decoded from the answer from the Bethe ansatz. So we have now a very explicit prediction for instanton amplitudes in the O3 non-sigma model. And I think it's a non-trivial challenge to reproduce this with instanton calculus. I mean, they are going, here you will face all these problems. You are going to have to consider off-shell configurations and so on. I don't know how to do this calculation in detail, but I think this is really one of the challenges for the future in understanding instanton calculus correctly. If we want to apply in gravity, we better understand it before in quantum field theory, and this is a proposal for how to go. Now, condensate calculus. This is the other alternative to non-perturbative effects. This has been extensively used in QCD phenomenology, and it should also be able to explain renormal singularities in general QFTs. But there have some hints in the literature that you might need a more general theory, in particular in calculations that we have done with Ramon and that Zoltan has also done. We have found that in some cases there are singularities appearing in the Borel plane which are not really fitting into the pattern that is expected from the theory of condensates of LBZ. So I think we really need to develop condensate calculus in these and other models, and maybe we have to generalize these ideas, and maybe there are non-perturbative effects which are not really accountable neither with instantons nor with condensates. So this is also something to consider. And so far, this is my last challenge. So far, I have focused on the coupling constant expansion. But what is very interesting is the 1 over n expansion. The 1 over n expansion is also an asymptotic series, which also will have 1 over n exponentially small corrections in 1 over n. And these are very important in string theory, and in particular in the context of the ACFT correspondence. But we don't know very much about the non-perturbative structure of the 1 over n expansion, except in the very simple case of matrix models. So one question is, can we use all these ideas to understand the non-perturbative structure of more complicated string theories? And maybe if we solve this problem of the 1 over n expansion in QFT, maybe with the help of the STFT correspondence, we can understand more general string theories with ADS duals and so on. Okay, this is all. Thank you very much for your attention.
Thanks for the very nice talk. Questions?
Question about the renormalons in supersymmetric theories. In n equal 2 theories, probably there are no renormalons.
Mm-hmm.
No? What about n equal 1? Do you know some examples?
I haven't looked at it.
Yeah.
I haven't looked at it, but of course, there are condensates in equal 1 theories. For example, there is the Gluino condensate and so on. So you might think that this leaves an imprint on perturbation theory that you could detect in some way. But I have to say that I have not really thought a lot about n equal 1 theories. This is something that I think should be done, because it might be one interesting intermediate step between purely non-supersymmetric theories and theories in which all these things are essentially trivialized. Okay, that's absolutely the case. Yes.
Just a question, like in string theory, there's a classic example of the R to the 4 coupling, where using duality and symmetry, supersymmetry, we know the full non-perturbative result. Can you also understand this non-perturbative corrections to the R to the 4 couplings using resurgence?
I think this has been even done. I think there are people like Dorigoni and Michael Green who have looked at this kind of examples. So, I think, in a sense, string theories on theories with some supersymmetry or theories which are sufficiently simple are the ideal testing grounds for resurgence, because this is where you will find, that everything is recovered from perturbation theory. So the hardest examples are, of course, asymptotical infer theories, even into dimensions and more realistic theories, yes.
Okay. So maybe they're even sort of trivial examples?
What do you mean a trivial example?
No, I mean, maybe this R to the 4 coupling is a trivial example.
No, I don't think it's trivial.
I
don't think it's trivial, and in particular, if I remember correctly, but I haven't really studied this in detail. But I think there is also a very interesting interplay with modularity, for example. Okay. So this is something that people have also tried to understand. You have some sort of, imagine they have an S-duality structure. You have a duality between tau and minus 1 over tau. What does this imply for the resurging structure, right? This is a natural question, because it has to be a constraint on the non-perturbative structure of the theory. So there is now a lot of also work in the direction of putting together resurgence and modularity constraints, which I think apply to this example that you're mentioning. Yes.
Thanks.
This question about something you mentioned in the last slide. What determines the singularities of 1 over n expansion in field theory?
Well, the singularities, I mean, as I said, the only example which we know very clearly is like matrix models, okay? So matrix models is another story that eigenvalue tunneling gives you large instantons. Now, there is a source of exponentially small corrections in the 1 over n expansion, which is just the Larsen, what I would call the Larsen dressing of a conventional instanton. If you have an instanton in a quantum field with a Larsen expansion, it goes like e to the minus 1 over g, and then when you go to the top coupling, it goes like e to the minus n over lambda. So this is the first term in the action of a Larsen instanton, which goes like e to the minus n times a non-trivial action of lambda. So in Larsen theories, one source is just, in the same way that to get the planar free energy, you have to resum all the planar diagrams, you have a conventional instanton, you have to resum all planar diagrams in the background of an instanton, and this gives you a Larsen instanton, okay? So this is a source of non-perturbative effects in Larsen theories. And in particular, Larsen instantons in matrix models are an example of this. But we don't really know very much about it. That's one source, but there could be others.
You said that in the case of this instanton business in QCD, you found there's a mismatch between position barrel singularities and those condensates?
Not in instantons, renormalons.
Excuse me, yes.
Yes.
So the position of barrel singularities in the case of QCD,
there is a general story that position of singularities, or renormal singularities, is an integer number divided by beta 0, right? Okay. Now, this is a very explicit calculus, and Zoltan can tell you about it, because it's actually, from the TVA equations, you can see very clearly that the location of singularities, when you calculate the free energy in the presence of a chemical potential for integrable models, is not there. Most of the singularities are not located there. Okay.
So that's my question.
Yes.
My question is that the position of barrel singularities is one-to-one correspondence with OPE structure.
Yes, exactly.
So are you saying you get something which contradictory with OPE?
No, not contradict directly, because this observable is in principle doesn't have an OP, it's a free energy. So it's not a product of operators.
But free energy has a lot of ambiguity inside.
It has?
It's ambiguous quantity. Depends how you regularize the short distances.
Yes, you have to do an additive normalization, and this might be the source of this. There are many people who are now trying to look at this problem. One way, for example, there is work in progress by Marco Serone and Thomas Reis, when what they are saying is that this chemical potential acts like a mass, and then the beta 0 gets changed because there is some sort of cutoff set by H, and then you have to, in a sense, this gives some sort of mass to some of the particles, and this changes the value of beta 0 and so on. So there are some sort of explanations around it, but I think what one should be able to do is a real direct OP calculation of this new non-perturbative effects. That's something that still has not been done.
But you believe, let's say, if I go from free energy to the correlation function, when you have very quite precise control of OP, those new singularity will reappear or not?
That I don't know. I want to leave this possibility open. I mean, I know that the OPE doesn't predict this, but I think the OPE has to be really, I mean, there are many few tests of this OPE idea. I have to say that there are very, very few tests of this OPE idea where you really know the answer and you can reproduce it with the OPE. I mean, people have used the OPE, but people have not really, not to my taste. I'm a mathematical physicist, okay? So I'm very picky, okay? So for my taste, there are still not sufficiently good tests of this idea of the OPE. And recently with Ramon, we wrote this paper with a test on Gros-Neve just to make sure that things work correctly in a two-point function, and there it works very well. But I still think, that this idea should be really tested in more detail in examples.
Once you mentioned Schiff-Weinstein-Zakharov,
Yes.
many years ago, they looked for the question, how does OP look like in Minkowski Euclidean space?
Yes.
And there's this claim, which hasn't been verified yet, and the structure of Barrett singularity will depend on the signature. It may happen going from Euclid to Minkowski space.
Yes.
In Minkowski space, we may have new singularity which is not visible in Euclid.
Yes, this is related to this quark-hadron violation of quark-hadron duality, right? Yes, this is actually related. I mean, this actually raises. I mean, let me reformulate this in a kind of more general way. I think the main problem there is that, you have all these trans-series. You have the perturbative series, the trans-series, but you might have an infinite number of trans-series. So if you do a resummation of each of these trans-series, you get usually a well-defined number, but you still have to sum the infinite number of trans-series. And this is still not clear that this sum is going to be convergent. So there might be another source of infinities apart from the factorial divergence, and this is actually related to this quark-hadron violation of quark-hadron duality that you were mentioning. And this is actually something which we still don't know very well what is going to happen and what are going to be the techniques to address this. Okay? So this is actually a deep problem from this problem, in the sense that we have at some point to address this problem as well. Now, in some examples, like for example the integrable models that we have been studying also with Zoltan, this problem does not arise. The trans-series sum is convergent. Okay? Or we have indication that it's convergent. So in that case, this problem will not arise. But in more realistic case, it might arise, and we might need a further generalization of this framework. Absolutely.
More questions?
Yes?
Just in the context when you describe your complex transassignments and you have your Stokes constants to represent integers, and you say this is related to the BPS counting problem.
Mm-hmm.
Do you think this is applicable? Can this be helpful in the index computations?
In the?
Index or superindex?
Actually, these BPS integers are an index. These BPS index, these BPS Stokes constants are the coefficient of an index. And this was one of the kind of surprising discoveries for us that, those constants, which look very crazy because they are these numbers that appear when you do this, eventually they make up an index.
But this applies just to this complex transassignments, or this
Actually,
is just topological class?
It also applies to topological string theory on Calabi-Yau. There also, the Stokes constants are integers. Of course, this is not a universal feature, and for example, Ricardo and his collaborators have calculated the Stokes constants for Pan-Levier 1, which describes 2D gravity, and there the Stokes constants are far from being integers, are all irrational numbers. So this is very specific to some types of theories. But it would be very interesting to know for which theories you have this sort of integrality properties and for which theories you don't have it.
When it holds, I see. Yeah.
One last question? Well, if not, let's start Marcos again.